There is a particular kind of desperation that produces genius. Not the comfortable desperation of a missed deadline or a shrinking budget, but the kind that comes when the walls are genuinely closing in, when raw materials have run dry, when bombs are falling on your factories, and when the enemy is coming from every direction. That is the desperation that gripped Germany in 1943 and 1944. And inside that desperate environment, the engineers at Junkers did something remarkable. They looked at the rockets being developed in German workshops, studied the turbopump and combustion principles Walter's engineers had refined through years of rocket propulsion work, and adapted what they found there to build something the world had never seen, the first mass-produced jet engine in history. This is the story of how Germany, running out of metals and time, reached across the boundary between rocket science and jet propulsion and pulled a new age of aviation into existence. To understand what Junkers accomplished, you first need to understand what they were working against. The Allied naval blockade, in effect since 1939, had systematically cut off German imports of critical metals, nickel, chromium, cobalt, tungsten, the exotic alloys that modern jet engines require to survive the extreme temperatures of high-speed combustion, were disappearing from German warehouses. Albert Speer, Hitler's armaments minister, was calculating in late 1943 how many months remained before reserves of certain strategic metals ran out entirely. The answers were not comfortable. Meanwhile, in a small engineering works along the Baltic coast in Kiel, a former shipyard engineer named Helmuth Walter had spent the 1930s perfecting something that seemed to have almost nothing to do with aviation. Walter was obsessed with highly concentrated hydrogen peroxide. When 80% pure hydrogen peroxide was forced over a catalyst, it decomposed almost instantaneously into superheated steam and oxygen at around 600 degrees Celsius. In the hot engine versions of Walter's system, that oxygen immediately combusted a second fuel, a hydrazine and methanol mixture, producing temperatures exceeding 2000 degrees Celsius and enormous thrust. Walter had developed turbopumps driven by this steam energy to pressurize his propellants, high-speed turbines operating in extreme thermal conditions, spinning fast enough to feed combustion chambers that burned hotter than almost anything else in existence. The Reich Air Ministry gave Walter a contract in 1936. By 1939, the Heinkel He-176 had become the first aircraft in history to fly under liquid-fueled rocket power alone. By the early 1940s, the successor to that work, the Messerschmitt Me-163 Comet, was emerging as the most radical interceptor Germany had ever attempted. It was powered by the Walter 109-509, a rocket motor, producing 3,300 pounds of thrust, capable of pushing the tiny aircraft to nearly 600 miles per hour. Nothing flying for the Allies could match it. And here is where the story of Junkers and rockets becomes inseparable. Starting in 1943, Junkers became the primary manufacturer of the Me-163 Billions airframe. Production responsibility had initially belonged to Clem, but quality problems were severe enough that the RLM transferred the entire program to Junkers. Junkers engineers were now building rocket aircraft, living alongside Walter's propulsion technology every day, understanding intimately what extreme combustion did to metal, how thermal stress cracked components, how cooling logic could keep a turbine alive in conditions that should have destroyed it. Junkers went even further into rocket propulsion independently. In 1944, the RLM called for a cheap, quickly produced rocket interceptor to defend German industrial targets. Junkers submitted a design called the P-1077 Julia, a small aircraft launched vertically by solid fuel boosters and sustained in flight by a Walter liquid rocket motor. The pilot lay prone inside the fuselage and would glide home after his powered attack. Two near-complete prototypes existed when the war ended. Simultaneously, Messerschmitt transferred development of an advanced Me-163 variant, the Me-163D, to Junkers, where it was redesignated the Ju-248. It was designed around an even more powerful rocket motor. Junkers built a full wooden mock-up shown to RLM officials in September 1944. This was the context inside which the Jumo 004 jet engine was born. Junkers was not a company that happened to be building jet engines. It was a company simultaneously immersed in rocket-powered aircraft, turbopump engineering, and high-temperature combustion, and the cross-pollination between those programs shaped every decision made on the jet engine side. The man responsible for the jet engine work was Dr. Anselm Franz, born in Schladming, Austria, in 1900. He held a doctorate from the University of Berlin and had spent years studying axial compressors and supercharger aerodynamics. When the Air Ministry pushed Junkers to begin a jet program in 1939, Franz received the assignment. He made one foundational decision immediately: he would not optimize for maximum theoretical performance. He would build an engine that could actually be manufactured quickly, in large numbers with the materials Germany actually possessed. The compression ratio was kept deliberately low. The combustion section used 6 separate cylindrical flame cans rather than a single efficient annular design. Simpler to build, simpler to replace. This was engineering for reality, not for textbooks. The first prototype, the Jumo 004A, was running on a test stand by 1940. By January 1941, it reached 9,000 RPM and 946 pounds of thrust. On July 18, 1942, a Messerschmitt Me 262 prototype lifted off under jet power for the first time, propelled by 2 Jumo 004A engines. Test pilot Fritz Wendel, who held the world piston engine speed record, described the sensation as unlike anything he had experienced. The aircraft seemed pulled into the sky. But the 004A was a demonstration, not a production engine. It used Tinidor alloy for its turbine blades, 30% nickel, 15% chromium, 1.7% titanium. Germany was running out of all 3 elements. The engine that could actually be built in quantity had to be redesigned around a completely different material reality. This is where what Junkers had learned from its rocket programs paid off directly. In Walter's hot rocket motors, combustion temperatures reached over 2,000 degrees Celsius, far beyond what any available alloy could survive through material properties alone. Walter's engineers had solved this through active cooling, circulating propellants through the walls of the combustion chamber, using the fuel itself as a heat sink before injection, managing gas flow to minimize direct contact between the hottest combustion products and vulnerable metal surfaces. This was not relying on better materials. This was engineering around material limitations through thermal management. It was exactly the approach Franz needed. The turbine blades of the Jumo 004 billions, the production version, were redesigned completely. Instead of solid billets of nickel alloy, they were hollow, fabricated from thin sheet metal folded and welded into an airfoil shape. The alloy was Chromodor, developed by Krupp, 12% chromium, 18% manganese, 70% iron. No nickel, far less chromium than conventional high-temperature alloys required. To keep these blades alive in combustion temperatures, they had no material right to survive. Franz's team applied the same cooling logic Walter's engineers had developed for rocket chambers. Compressed air bled from the compressor was channeled through the hollow interior of each blade, carrying heat away before it could penetrate deep enough to cause damage. The combustion chambers themselves were changed to mild steel sheet, aluminum coated for surface protection. The entire hot section was rebuilt around active thermal management rather than material resistance. The result worked. It was not perfect. The turbine blades had a design life of around 25 hours before major overhaul, but it worked. Pilots who advanced the throttle too quickly would spike combustion temperature before airflow could respond, damaging blades and risking engine failure. The Jumo 004 billions demanded careful, precise handling. In experienced hands, it was manageable. In the hands of half-trained pilots rushed through abbreviated programs as Germany desperately filled cockpits, it was unforgiving. A blade vibration problem returned in late 1943, cracking turbine blades unpredictably. France brought in Max Bentel, a resonance specialist. Bentel determined that a natural resonant frequency of the blade design fell within the engine's operating range, creating harmonic stress accumulation until fracture. His fix was precise: shorten each turbine blade by 1 millimeter, reduce maximum operating speed from 9,000 to 8,700 RPM. Small numbers. Critical effect. The cracking stopped. The Jumo 004 billions entered production in early 1944. Almost immediately, the factories producing it began moving underground. Allied bombers were systematically destroying German aircraft production from above, and Speer's response was to carve factories into hills. In the Harz Mountains of central Germany, a tunnel system originally built for fuel storage was converted into the Mittelworks. The northern section was dedicated to jet engine production. Approximately 2,400 Jumo 004 engines were built there by war's end. The Mittelwerk ran on forced labor drawn from the Dora Mittelbau concentration camp. Over 20,000 people died at Dora under starvation, disease, overwork, and deliberate brutality. Workers performed acts of sabotage, rocks placed between fuel tanks and brackets, contaminated adhesives, small acts of defiance from people who had everything taken from them. The engineering Franz achieved was real. The human cost that made mass production possible was equally real. If you are finding this history as gripping as we do, this is the moment to subscribe to the channel and hit the notification bell. We go deep into the hidden stories behind the machines that shaped the modern world, and this one is far from finished. The Me-262, powered by two Jumo 004 Billions engines, began entering Luftwaffe service in the summer of 1944. What it offered was transformative. The P-51D Mustang, the finest Allied piston fighter, reached approximately 437 miles per hour at optimal altitude. The Me-262 exceeded 540 miles per hour. That 100-mile-per-hour gap was not marginal. That 162 pilot who chose to disengage could simply accelerate away. On July 25, 1944, around most Allied fighters. Simultaneously, Junkers produced Me-163 Billions Comets were flying combat missions from Brandis, near Leipzig, defending the Leuna synthetic oil refinery. On July 28, 1944, the rocket interceptors made their operational debut against American B-17 formations. American escort pilots watched in astonishment as the comets flashed through the formation at speeds no P-51 could approach. The jet age and the rocket age arrived in German skies almost simultaneously, and Junkers had a direct hand in both. Why didn't this convergence of technologies save Germany? The answers compound on each other. The Jumo 004 Billions' short service life drained resources in constant overhaul cycles. Pilot quality had collapsed. Germany's experienced aviators from the early war years were dead or exhausted, and the men being pushed into Me-262 cockpits in 1944 lacked the hours to handle the engine's sensitivity. Allied commanders quickly identified that the Me-262 was most vulnerable at low speeds during approach and landing, and organized fighter sweeps timed to attack the jets in their most vulnerable moments. The Luftwaffe built elaborate flak corridors along landing approaches and maintained piston fighter top cover over their jet bases just to let their own aircraft land safely. Hitler made the situation worse. In 1943, he became convinced Germany needed a high-speed jet bomber more than a jet interceptor. The Me-262 was adapted to carry two 551-pound bombs in a version called the Sturmvogel. Resources were diverted. Deployment of the pure fighter version delayed by months. By the time the Me-262 fighter was available in meaningful numbers, Normandy had already succeeded, Paris had been liberated, and Romania had switched sides in August 1944, denying Germany access to the Plesty oil fields that had supplied a substantial portion of its aviation fuel. Without fuel, the performance specifications of jet and rocket aircraft became irrelevant. The United States Strategic Bombing Survey concluded after the war that even earlier Me-262 introduction with experienced pilots would have inflicted sharply higher losses on Allied bomber formations, but would not have changed the fundamental outcome. The industrial disparity was too vast. What the jet and rocket programs did accomplish was something more durable than tactical victory. They proved that reaction propulsion, whether through rocket exhaust or jet turbine, was not a laboratory curiosity, it was the future of flight. When Allied forces arrived in Germany in 1945, teams of American, British, and Soviet engineers moved quickly to secure everything. At Dessau, complete Jumo 004 documentation was found alongside several loose engines. The Soviets reverse-engineered the engine as the R&D-10, which powered their first operational jet aircraft, the Yak-15 and Yak-17. Walter's rocket technology was studied extensively and formed a foundation for understanding high-pressure turbopumps that would eventually inform ballistic missile and space launch propulsion. Anselm Franz was brought to the United States under Operation Paperclip. He joined Lycoming Engines in 1952 and spent 16 years at the frontier of the technology he had helped create. He led development of the T-53 turboshaft engine powering the Bell A-1 Huey, the helicopter that defined the Vietnam War era. He worked on the T-55 for the Chinook. He contributed to the AGT-1500 gas turbine of the M1 Abrams tank. He is credited with developing what is recognized as the world's first high-bypass turbofan engine, the fundamental architecture underlying every large commercial airliner flying today. He retired in Stratford, Connecticut, and died in Stratford. The Jumo 04 Billions sits in museums today, at the National Air and Space Museum in Washington, at the Deutsches Museum Aviation branch in Schleißheim. Nearly 4 meters long, weighing 745 kilograms, producing 1,980 pounds of thrust. 8 compressor stages, 6 flame cans, 1 turbine stage, hollow manganese steel blades cooled by compressed air. Surviving temperatures they had no material right to survive, because engineers borrowed the thermal management logic of rocket propulsion to keep them alive. Every axial flow jet engine in the world follows the same fundamental architecture. Every hollow, air-cooled turbine blade traces its lineage through a chain of development that includes this engine and the desperate, brilliant, morally complex choices that produced it. The contrail you see crossing the sky overhead carries the engineering DNA of what junkers built in underground tunnels in the Harz Mountains, informed by the rocket science being developed in the same company at the same time. That is not a simple legacy. It carries the weight of every choice made to build it, and every life lost in the building. Understanding it completely, the ingenuity, the desperation, the human cost, the lasting consequence, is the only honest way to understand where the modern world came from. If this documentary moved you, please like this video and subscribe to the channel. Leave a comment telling us which part of this story surprised you most. We read every one, and your support makes these films possible. Thank you for watching.